Hello Teacher School, my name is Nguyễn Văn Nam. In this video, I will walk through question 4, building a softmax regression model completely from scratch to classify fashion managed images. My student ID is E2570795. So my variables are x equal to 95, y equal 35, and z equal to 2. So we train for z equal to 2 epochs using pure NumPy, no NN linear, no high-level layers. Fashion managed is a standard benchmark dataset containing 70,000 grayscale images of size 28 by 28 spread across 10 clothing categories. After filtering, we only keep two classes, sandal and shirt. This gives us 12,000 training samples and 2,000 test samples, perfectly balanced at 6,000 per class in training and 1,000 per class in testing. On the left in blue, you can see sandal samples, flat open footwear with a very distinctive silhouette. On the right in green are shirt samples, rectangular purported clothing. Even visually, these two classes look very different from each other. That's an important observation. It hints that a simple linear model should be able to separate them well. Each image is flattened from 28 by 28 into a single vector of 784 pixel values, which becomes the input to our model. This slide shows the full architecture of our softmax regression model. The input is a flattened image of a vector of 784 pixel values. I manually initiate two parameters, a weight metric W of size 784 by 2 and a bias vector B of size 2 that gives us only 1,570 parameters in total, and critically no pre-pure layer was used. The forward pass works like this. We multiply the input x by w and add bias b to get vector code the logics. Z equals x times w plus b. The logic are two raw scores, one for each class. We then pass the logic through the softmax function, which converts them into probabilities. The output is two positive numbers that sum to 1, representing how confident the model is that the image is a sandal or a shirt. The loss function is cross entropy. We take the negative mean of the log of the predicted probability for the correct class. The smaller the loss, the more confident and correct the model is. For backpropagation, the gradient of the loss with respect to the logics has a clean closed form. It equal to the predicted probability minus 1 hot encoding of the truth label divided by the batch size. From there, we compute gradients for W and B, then update using stochastic gradient descent with a cleaning rate from 0.1 and batch size of 256. This is the code that I use to train the model. I will try to run. You can see after training the model, there are two images that are generated, and I will go back to the slide. Here are the training result for two epochs. In epoch 1, the training loss is 0.1138 and the validation accuracy already reaches 99.5%. In epoch 2, the loss drops further to 0.0404 and the accuracy improves to 99.6%. This is remarkably fast convergence for just two epochs. The explanation lies in the concept of linear separability. Sandal and search occupy very different regions in the 784 dimensional pixel space. So a single linear decision boundary is enough to separate them almost perfectly. To put this in perspective, if we had chosen a harder pair like t-shirt versus shirt, which look visually similar, a simple linear model would struggle in, and we would need deeper non-linear architectures. Here we visualize 16 randomly selected test samples. A green border means the model predicted correctly, and a red border means it made a mistake. As you can see, almost all borders are green. This is consistent with our 99.6% accuracy. The model confidently distinguishes the flat, thin of sandals from the taller, more rectangular shape of shirts. Any misclassifications that do occur tend to happen on ambiguous images. For example, a sandal photographed at an unusual angle or a shirt with a very similar piece or pattern to a sandal. Let me summarize what I did. First, using student variables is equal to 95, y equal to 35, z equal to 2. I selected class 5 sandal versus classic shirt from the dataset fashionist. I built a softmax regression model entirely from scratch in NumPy, manually initializing the weight matrix W of size 784 by 2 and bias B of size 2, totaling only 1,570 parameters. I trained for 2 epochs using stochastic gradient descent with learning rate 0.1 and pass size 256, achieving a final validation accuracy of 99.6%. So the key takeaway from this exercise is that model complexity should match the difficulty of the problem. When the two classes are visually and statistically well separated, as sandal and search are in pixel space, even the simplest possible model achieves near perfect performance. This reinforces a fundamental principle in machine learning. Understanding the geometry of your data is just as important as the choice of your architecture. I think this is the end of my presentation. Thank you, teacher.